So we begin with the soil dynamic, okay, as a introduction, okay, before we discuss on the formulation of the shallow foundation, deep foundation, and also the uh, retaining or lateral stress. Okay. Okay. So the contents we cover on the introduction, okay, soil structure interaction, we call as a SSI, wave propagations in soil, and the last one we discuss on the stabilization of ground for geotechnical structure. Okay. Okay. So as we know, it's very important, okay, for us to learn, okay, on the geotechnical engineering, okay, where we understand that most of the structure, okay, that we build, okay, will be uh, sit on the ground, okay. Start from the natural slope, okay. So we need to check for the stability, okay. Let me use the curse, the highlight. Okay. From the natural slope, then we do a cutting, okay. For example, if you want to develop the area, want to build roads, okay. So we do a cutting, so we have disturbed this slope, so we consider as a man-made slope, okay. Then human build a dam, okay. So this dam either it is a earthen dam, okay, or a concrete dam, okay. So this dam still sit on the ground, okay. So then we have a building foundations, okay. Either we use a shallow foundations or deep foundations, okay. So it still sit on the ground, okay. Then for example, to build what we call as a basement, okay. So we need to have this kind of brace cut system, okay. So you also may learn on the design of the brace cut, okay. So under a static loads, okay. Or you can include later on the effect of the lateral stress, okay, due to the seismic load, okay. So this is support excavation. Then we go for a tunnel, okay, to have a trenchless approach, okay, trenchless approach. Then road embankment, okay. So this is a common type of road platform, okay, where we build a road embankment, or we can also use to build for a railway tracks, okay. So then we have constructions on the soft soil, okay, for example, to build a harbor, okay, nearby the sea level, seaside, okay. So the last thing will be on the offshore foundations, okay, where they build uh, offshore platform, okay, and rest on the ground itself, okay. So it means that all civil engineer begin with geotechnical engineering, okay, except for one structure or one what we call as one yeah, big structure, okay, that not really rest on the ground, okay, but it consists a lot of bedroom, swimming pool, okay, which is what we call as the like Titanic, okay, that the ship that have a lot of that have a hotel inside it, so they not rest 100% on the ground, okay. Okay, so as a geotechnical engineer, okay, so we may deal with the laboratory testing, okay, to get all the informations, okay, on the site, okay, that we are deal, okay, this is the construction site, for example, okay. So then we get the informations of the soil, okay, and then send for the lab, okay, to gain the soil properties, okay. Then we may use all the result, okay, from the lab test, okay, for the design purpose, okay, so for design and analysis, okay. So then this routine, okay, this work will be continue, okay, by constructing whatever structure, okay, on the ground, okay, resting on the ground, okay. So this is a cycle for a geotechnical project, okay. So it's very important for us, for example, to know what will be the soil properties, okay, that we may use in the design. Either we use a software or we use a hand calculations. Okay, so for the uh, design process, okay, so we may check for the two element, okay, which is the feasibility. For this part, okay, it involves a settlement, okay, a tilt, okay. So we feel uncomfortable, okay, to sit or to rest inside the building, okay. So due to this problem, we may find that there are some crack, okay, or whatever uh, damage on the structure, okay. However, the structures still can provide a service for the people to stay inside, okay. Then we call it is a serviceability that feel only uncomfortable to rest in the building, okay. So this example for a tilt building, okay, which is a pizza. So we can find that the building is tilt, okay, on one direction, okay. And actually in Malaysia we also have one building, okay. They also show a tilt towards to the other side, which is in Teluk Intan, Perak. Okay, so no need for you to go to Italy. Okay, just need to spend some money to go to Teluk Intan. Okay, I have experience went to Teluk Intan. Okay, so then I climb up to the what we call to the top of the tower. Okay, on the top of the tower, there are clock. There are big clock. Okay, so the same clock with the one that display in Kuala Lumpur. Okay, Sultan, what we call Sultan in Kuala Lumpur building, near to the Dataran Merdeka. Okay, so the guy that cut the the tower, okay, has shown to me how to use the clock, okay, that we need to manually lock the clock, okay, by using a handle, okay, then twist the handle, so then the clock continuously run, okay, for another 1 or 2 days. Then they need to twist again the lock, okay, to make sure that the clock will be continue run for the next following days. Okay. So then another part for the geotechnical engineer should consider in the design is the failure, okay, where this is not acceptable value that should be considered in the design, okay, where it can make the what we call as the building collapse later on. Okay, so this an example of one of the building that will be collapsed, okay, due to the failure, okay, on the ground itself. Okay. So as a geotechnical engineer, okay, so we need to design properly, okay, to avoid for this kind of problems, okay, especially for the uncomfortable conditions when somebody want to rest inside the building. Okay. So traditional soil mechanics and geotechnical engineering design was predominantly concerned with soil strength and the stiffness of the soil, okay, so that the design engineer could define the failure state of the soil and or control excessive deformations of the soil structure. Okay, so these excessive deformations, okay, is under the serviceability, okay, while the failure is under the failure collapse state. Okay, so normally we may use the soil strength and the stiffness, especially when we want to carry out for the design, or we want to use whatever software, okay, to identify, um, for example, what would be the capacity that could be sustained by the soil itself. Okay, so in this circumstance, the loading is considered static and the strain imposed within the soil may vary from about 10 power by negative 3, okay, in service to a few percent at failure. Okay, so the strain play the important criteria, okay, for the make sure that the building, or sorry, for any structure rest on the ground, okay, should able to perform well either in the service or in the before it reach at the failure condition. Okay, so many circumstances that where cyclic or dynamic load are applied to the soil, but either by natural forces such as earthquake. Okay, so this is some of the example of the dynamic loads. Okay, so we have here earthquake, wind and water waves, or from man-made sources such as bomb blast, traffic loads, and machine foundations. Okay, so this is an example of the cyclic loads, okay, that commonly occur, okay, in our area, okay, but in terms of the magnitudes, most probably it's not very higher. For example, for the seismic, okay, because we are out from the ring of fire, because we are not in the ring of fire. Okay, for example, in Indonesia, okay, area, okay, it located in the ring of fire, okay, compared to the Malaysia, so we are far from that area. Okay, however, we still experience some of the earthquake effect, okay, which is occur at the Indonesia area. Okay, then we have a wind and water wave, okay, that still contribute to the dynamic loads on the building and then make a problem to the ground. Okay, and also we also have a man-made sources such as bomb blast, especially on the quarry site. Okay, so where they use an explosive, okay, to yeah, to get the rock, okay, to be used as a part of their business. Okay, so then we also have an effect on the traffic load. Okay, and the last one is from the machine foundations. Okay, we may discuss on the machine foundations. Okay, on the deep foundation. Okay, where most of the example is related to the vibration from the machines. Okay, so the type of the dynamic load in soil or the foundation of a structure depends on the nature of the source producing it. Okay, so dynamic load varies in their magnitudes, directions, or positions with times. Okay, here we have a periodic loads. Okay, where it's a special type of load that varies in magnitude with time and repeats itself at regular interval. Okay, for example, operations of reciproc reciprocating or a rotary machines. Okay, so it is a routine operation. Okay, so we call it as a periodic load. Okay, while for a non-periodic load, those load they are not show any periodicity. For example, wind loading on a building. Okay, so there will be loads that we know that in routine. Okay, for example, 8 to 5. Okay, they will operate any machine. Okay, so there is a predict load. Okay, however, for the event that we doesn't know when will be the event will be occur. Okay, so we call as a non-predict loads. Okay. So deterministic load are those load that can be specified as a definite function of time, okay, irrespective of whether the time variation is regular or irregular. For example, the harmonic load imposed by unbalanced rotating machinery. Okay, so we know that these problems happen. Okay, so we can identify what is the value comes from this machine. For example, these rotating machines. Okay, so non-deterministic load are those load that cannot be described as a definite function of time because of their inherent uncertainty in their magnitudes and form of variation with time. For example, earthquake loads. Okay, this is a load that we cannot control. Okay, we cannot easily um, control it. Okay, yeah, definitely the earthquake we cannot control it easily. We cannot control the time. Okay, so it's happened in sudden. Okay? So cyclic load are those load which exhibit a degree of regularity both in its magnitudes and frequency. So it has its own frequency. Okay, with a constant magnitudes. Okay, normally a machine. Okay, when we operate a machine, okay, it will provide cyclic loads. Okay, and static load are those load that build up gradually over time or with negligible dynamic load. Okay, so static load is a common load. Okay, without any effect of the dynamic load. Okay, then it will maintain, stay at the at and rest on the soil. Okay, for over a time. Okay. Okay, so this example of cyclic load. Okay, low speed rotary machines. Okay, so we know the magnitudes of the load. Okay, and then it show a cycle of the loads with the time. Okay, so single impact of hammer and vertical acceleration due to the pile driving. Okay, so this example, for example, we may use a pile dynamic analysis PDA. Okay, so we apply a impact of the hammer, and then we may look on the feedback of the of the of the of the seismic. Okay, to understand what is the capability or capacity of the pile. Okay, so then the last one is the Axillogram of Earthquake. Okay, so this is the earthquake acceleration. Okay, where normally been measured in gravity force. Okay, so then it may reduce with time. Okay, so at the first stage the value is very high, and then it may reduce with towards the times. Okay, so this is some example, okay, of the dynamic load. Okay, where it has a different in terms of the behavior, in terms of the magnitudes, in terms of the frequency. Okay. So the magnitude of these dynamic loads are generally much smaller. than more static loads and generate strain within the soil as low as 10 power by -6. Okay, so for the static load, okay, the strain value, okay, at the what we call it at the serviceability is around 10 power by -3. Okay, but for the failure, okay, so if we go up to 10 power by -1 or until 1, okay, so it can produce a large strain and it show a yield of failure condition. Okay. Although the magnitude of these dynamic loads are often much smaller than static load, okay, the problem is on the initial force may become important and must be considered in geotechnical design. Okay. So as we can see in this diagram, okay, so we have here a dynamics problems and a static problems. Okay, so the dynamic loading can be defined by two characteristics, which are loading frequency, okay, and the number of the load cycle. Okay, so generally dynamic problems are where the cyclic load is applied at a frequency greater than 1 Hz or 1 cycle per second. Okay, so sorry. Okay, for example, this is the one complete cycle. Okay, so we need to count how many cycle per second. Okay, depending on the loading event, the number of cycle can vary from single load, okay, such as those generated by bombs or blasting. Okay, so the blasting it only occur for one cycle only. Okay, up to many thousand of cycle as in a machine foundation vibrations. Okay, so problem with dynamic load can be divided, okay, uh, into three categories area based on the number of the load cycle. Okay, so for the first one we categorize as an impulse load, okay, which is only have a single short cycle. Okay, where a single impulse or of short duration occur. Okay, then we have a vibrations, okay, or wave propagation generally applied to earthquake event and construction activity where a number of loading cycle occur, okay, within 10 to 1000 at frequency from 1 to 100 Hz. Okay, so it has capability to cycle up to 10 power by 3. Okay, so where the number of the cycle uh, can consider as a large, okay, which is from 10 power by 3 to 10 power by 5, okay, as though associated with the machine foundation, okay, and traffic loading. Okay, so in this case the soil behavior can be considered as potential fatigue related. Okay, so because it's the cycle is very is the cycle is the cycle is large, so when it's exposed so many times, so it can potential to have a fatigue relic. Okay, so for the static problems, okay, so we can consider uh, the what we call the structure, okay, rest on the soil, okay, and it will gradually provide stress, okay, over the time, okay, without having any dynamic problems. Okay, so on this figure, okay, uh, what we can learn from this figure, okay, there are number of the shear strain, okay, from the 10 power by negative 4, okay, until it greater than 1, okay. So for example, for a normal type of static behavior or static load, okay, so under the failure strain, okay, the failure or the strain value is around 1 to power 1 to or greater than 1. Okay. So for the condition, okay, where the soil experience a settlement, okay, or the visibility, okay, so it may experience under the range, okay, from the elastic to the viscoelastic plastic, okay. Okay. So then for the last one, okay, which is from yeah 10 power by negative 6 to 10 power by negative 4, okay. So this it respond as a linear elastic, then it can consider as recoverable material, okay. So there is no permanent deformations, okay, on this part, okay. Okay, at this strain, both the number of the loading cycle and the rate of loading have a negligible effect on the soil behavior. Okay. So from 10 power by negative 4 to 10 power to negative 2, okay, the soil is elastoplastic and irre irre irrecoverable, okay, permanent deformation occur, usually associated with crack and diffraction settlement of structure supported on soil. Okay, so this is more related to the settlement. Okay, and the cost to the structure, it will have a crack on the structure itself. Okay, so at this strain, the number of the loading cycle and the rate of loading both have an effect. Okay. So these six levels are typically for a number of geotechnical structure such as retaining wall, tunnel, and deep excavations. Okay. So the last one is the higher strain, okay, where I have discussed before, okay, where it exhibit failure, where the strain increase with no further increase in shear stress, okay. So these are typically associated with slope failure, compaction, and liquefaction of non-clay soil. Okay. So in order to uh, to examine, okay, the behavior of the soil, okay, so we need to include, okay, or we need to determine uh, the key parameter of the soil properties, okay, which is the shear modulus G and the damping, okay, at this range of uh, strain value, okay. While in the designing for the failure condition, okay, so we may use the friction angle and the cohesions in the design, okay, that normally we can obtain from a normal triaxial test, okay. So for the small strain condition, okay, so this is some of the example, okay, the measurement device, okay, that can be used, okay, to obtain this shear modulus and the damping value, okay. For example, if we are carry out for the in situ measurement, okay, so we may use the seismic wave methods, in situ vibration test, and then we also can use the repeat load testing. Okay, so all this method, okay, can obtain, okay, for the value under a small strain, medium strain, and large strain. Okay. Then for the laboratory measurement, okay, so we have here wave propagation, we call as a bender element. Okay. So for the bender element, normally we use to gain the properties under the small strain. Okay. Then we have a resonant column test, okay, which is it cover from the small strain to the medium strain. Okay. Then we also have a monotonic or cyclic loading. Okay. Uh, for example, by using the triaxial setup, okay, so we can apply either a monotonic, okay, which is under static, or a cyclic, okay, or dynamic loading. Okay. So the last one is the repeat load test. Okay. So in our lab, in geotechnical lab, okay, so we have here a bender element, okay, that could get the value for the small strain, and also we have a cyclic, uh, what we call a cyclic triaxial, and also a static, or the normal triaxial testing. Okay. So if you want to further for example, for your master project, okay, so you can use this device, okay, to obtain the value for the shear modulus G and damping, and also to obtain the friction angle and also the cohesions. Okay. Okay. So the problem with the dynamic loads, okay, so although the magnitudes is considered as low compared to the static value, okay, it has a problems on the inertia. Okay. So what is the inertia? Is the tendency of the object to resist being moved, or if the object is moving, to resist a change in the speed of direction. Okay. So a simple analogy that we can make, okay, for example, okay, if you drive a car, if somebody drive a car and then you are the passenger in the car, okay, so let's say the driver uh, have a sudden stop, okay, so you can feel that you are moving in front, okay, and for example, if the driver is sudden move, so you can feel that you are moving back. Okay. So that is the simple explanation on the initial force. Okay. So Newton first law said that the object do not accelerate spontaneously. Okay. So this property of matter which cause object to resist acceleration is named as inertia. Okay. So in Newton first law is often called the law of inertia. Okay. So this example of a of a building, okay, and as a sudden acceleration on the soil, okay, so it made the foundation, the what we call the building start to move, okay. So that's why in some country, okay, they put a damper, okay, on the building, okay, to minimize the effect from the acceleration or from the seismic. Okay. Sorry, can I have 1 minute because I have a call? Okay. 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 Most of the civil engineering structure involves some type of structure element with direct contact with ground. Okay. So when the external force such as an earthquakes act on this system, either the structure displaced or the ground displacement are dependent of each other. Okay. So even though the foundation structure and the supporting soil are two different physical entities, okay, they form a system. And in terms of the mechanics of behavior of such systems, one component influences the behavior of the other, the end product being the result of this mutual action or interactions between the two. Okay? So this is the essence of soil structure interaction. Okay. So this is the concept of soil structure interaction. Okay. Especially on the event of the earthquake. Okay, when there is a movement of the ground. Okay. So actually, the soil have a great interaction with the structure. Okay. So uh, in terms of design, okay, so need to consider, okay, the interaction of this soil structure interaction in the design stage. Okay. Previously, most of the designer not include this kind of soil structure interaction in their design. Okay. So right after an event, if I'm not mistaken, we go through, okay, in the Kobe event, okay, the Kobe earthquake event in 1995, so they have improved the standard, okay, where they include this kind of soil structure interaction, okay, in their design, okay, after the Kobe event, okay. So this process in which the response of the soil influence the motion of the structure and the motion of the structure influence the response of the soil is termed as soil structure interaction. Okay, they call as SSI. Okay, so conventional structure design method neglect the SSI effects. Okay, neglecting SSI is reasonable for light structure. Okay, we can easily neglect for when we design for a light structure. Okay, in relatively steep soil such as low-rise building and simple rigid retaining wall. Okay, however, the effect of the SSI is very important or prominent for heavy structure resting on relatively soft soil. For example, nuclear power plant, high-rise building, and elevated highway of on soft soil. Okay. So in here we have two conditions, okay, where first the building load is very huge, okay, or the load is very high. Sorry, the building is very high, okay, and the second thing is the structure or the soil is very soft, okay, so it can contribute to the defect, to the failure of both building and structure. Sorry, building and soil. Okay. However, for light structure, okay, and rest on a very stiff soil, okay, so it's not very important, okay, to include the SSI in the design. Okay. So the lesson is, okay, first I either the first task is to improve the condition of the soil, okay, where I will discuss later on, okay, on how to improve the soft soil condition, okay, to reduce the effect from the vibration from the seismic, okay. The second thing is to improve the behavior of the structure, okay. For example, by applying a damper, okay, in the structure, okay. For example, for the long span bridge, okay, normally they use a rubber damper, okay. When I went to second Penang bridge, okay, so I can see a rubber damper, okay, between the bridge structure and the pier of the bridge, So they use what we call as a rubber damper, okay, made from rubber, and then uh, it can reduce or it can minimize, okay, the effect from the uh, from the from the acceleration of the soil. Okay, so when I went to Hokkaido, okay, in Japan, okay, I can see a lot of building that they use a damper system to reduce the effect from the earthquake. Okay. So damage sustained in the recent earthquake, such as the 1995 Kobe earthquake, have also highlighted that the seismic behavior of structure is highly influenced not only by the response of the superstructure, but also by the response of the foundation and the ground as well. Hence, the modern seismic design code, such as standard specification for concrete structure, seismic performance verification, JSCE 2005, stipulate that the response analysis should be conducted by taking into consideration a whole structure system, including superstructure, foundation, and ground. Okay, so until 2005, okay, they start to implement the SSI in the design. Okay. So the process in which the response of the soil influence the motion of the structure, and the motion of the structure influence the response of soil is termed as a SSI. Okay. So stiffness relates increment of stress and increment of strain. A knowledge of soil stiffness is required to calculate ground movement and to obtain solution to problem of soil structure interaction, such as load on retaining wall. Okay, so this is just one of the example. Okay, so we need to what we call as to have informations on the soil stiffness. Okay, to include or to calculate the ground movement. Okay, in the soil structure interaction. Okay. So this some of example, okay, on the soil structure interaction. Okay. So when an earthquake occurs, the building and the ground vibrate with influencing each other. Okay. So this phenomena is called dynamic soil structure interaction and is recognized as being very important for seismic design of structure. Okay. So this is the earthquake wave. Okay. Then we have a soil. Okay. Then this is the foundations, while this is the main superstructure. Okay. So the role of the foundations, okay, under normal condition, supporting the dead weight and the life load of the building, and then transmitting this load to the ground. Okay, but during the event of the event and of an earthquake, transmitting the ground motion to the building. Okay, bearing the building vibration and transmitting them to the ground. Okay, so means that the the wave from the earthquake, okay, will be transmit to the building from the what we call from the foundation, and the vibration from the building will be transmit by the foundation to the ground. Okay, so means that the wave will be go through to the building from the foundation, and then from the foundation from the go through to the building foundation, and then the building will later on transmit the foundation, transmit the wave to the soil from the foundation. Okay, the ground and the building influence each other through the foundation, and this is called as a dynamic soil structure interaction. Okay. So the degree of influence of SSI on response of building depends on stiffness of ground. Okay, dynamic characteristic of the building itself, that is natural periods or damping factor. Okay, So the last one is the foundation types. Okay, so this is some of example of a common foundation type. Okay, so first we have a spread foundation or shallow foundation. Okay, so then we have pile foundation without basement. Okay, so this is the common pile foundation. Then we have a basement without pile. Okay, so the last one is a basement with pile. Okay, so the position where the SSI take place, okay, for the first one through the bottom surface of the foundation. Okay, so it may happen on the bottom part of the foundation. Okay, through the pile foundation. Okay, so it will transmit the wave. Okay, through the pile. Okay, while for the basement, okay, it will transmit from the base and to the side wall. Okay, and the last one through the base surface and the pile. Okay, so the influence of the SSI become remarkable and more complicated as the amount of contact between the ground and the foundation increase. Okay, sequentially in order from A to D. Okay, so the simple one is the A, and then when it comes to pile, so it become a little bit complicated and more complicated and most complicated for the basement pile. Okay. So okay, we may relate with the event of the earthquake. Okay. Uh, from this diagram. Okay. So the interaction between ground and building during the earthquake event, okay, when the seismic wave, they call as a E naught, okay, generated by the earthquake fall, okay, okay, by the earthquake fall, reach the bottom of the foundation, okay, they divided into two types, okay. The first one is the wave E1, okay, which is entering into the building, okay, and the wave F naught being reflected back into the ground. Okay, so this is the F naught. So the wave, okay, will be transmit to the foundation, and then from the foundation, okay, it may transmit to the building, okay, and named as a E1, and at the same time there will be a wave reflect back to the ground for the F naught. Okay, the wave E1 is called the transmission wave, while the wave F naught is called the reflection wave. Okay. So the transmission wave entering into the building travel towards the top of the building with subjecting the building to vibrate. Okay. So it go up, okay, and then start for the building to vibrate. Then they reflect at the top and travel back down to the foundations. Here, a crucial phenomenon occurs for considerations of the SSI. Okay, as I told you previously, the role of the foundation during the earthquake, okay, where the load, where the wave from the earthquake, okay, transmit to the building, and then the vibration from the building transmit to the ground. So when the waves that are reflected at the top of the building and traveling down, F1, reach the foundation, a part of them is transmitted into the ground while the rest is reflected back again and one start to move upward through the building. Okay, so this is called the cyclic effect. Okay, so some part has been transmitted to the foundation and some parts still remain in the building. Okay, so the former wave escaping into the ground are called as radiation wave. Okay, so when the amount of these radiation waves are small, the seismic wave once transmitted into the building and the building continue to vibrate for a long time. Okay, the apparent vibration condition become the same of the small damping of the building. Okay. The damping caused by escape of the seismic wave which has been transmitted into the building back into the ground is called as radiation damping. Okay. So that is the cycle. Okay. When the earthquake event happen. Okay. So until the amount of the radiation wave are small, okay, so at the end it will be become at a normal condition. Okay. So when the building foundation is forced to vibrate vertically, okay, a stress called contact earth pressure is caused at the boundary between the bottom surface of the foundation and the ground. Okay. So the distribution of this contact earth pressure over the bottom surface of the foundation is called as the contact earth pressure distributions. Okay. So this is the common type of distributions earth pressure with a normal, what we call it, with a normal static load. Okay. So the three type of distributions. Okay, we have a rigid foundation. Okay, we have a uniform soil classification, and then we have a parabolic distribution. Soil non-linearity are observed. Okay. So for foundation and substructure solution with an increased complexity, more involved method of calculating the force within and displacement of the structure element are required. Okay. The use of the more basic approach that really rely heavily on the hand calculation order of time may not be appropriate. Okay. In such situation, as there may be too many degree of indeterminacy within the problems, or they may simply too time consuming to use. Okay. So later on, the use of the finite element model allow the user to create source structure model of the whole or part of a problem with relative ease. Okay. So we can do a calculation by using the manual formulation. Okay. However, when it comes to a very complex situation, definitely by using the finite element will be the best solution. It is same with the slope. For example, slope problems. Okay, we learn on the method of slices. Okay, at the end, the reference book suggests to use the software because it's very complicated to determine the most optimum value for the factor of safety, okay, by using a hand calculation. Okay. However, we still need to understand, okay, the concept, okay, or the formula uh, relate to any problems, okay, before we use the software to solve it. Okay. So this model can generally then be modified to respond to change in a design or undertake parametric study that might otherwise take a great deal of time. Okay. So source structure model can also provide us with a means of predicting the impact of one structure on another. Displacement and stress change can be calculated for different construction phase. Okay. So at the end of the what we call of the analysis, okay, so we can identify what will be the displacement and what will be the stress changes, okay, due to this SSI approach. Okay, because at the end we want to determine the capacity of the soil, and also what will be, is there any huge displacement occur, okay, due to this SSI, due to this effect. Okay, so under the wave propagation in soil, okay, there are three types of wave are readily encountered and are of importance. Okay, so if you want to what we call as to determine the type of wave. Okay, so three type of wave which is very important. Okay, where we have a P wave. Okay, we call as a compressional wave, and also we have a shear wave. Okay, and another one we call as a relic wave. Okay, so this value, okay, that we can get from the soil, okay, can be used, okay, to determine, for example, the value for the shear modulus, for example. And then this value of shear modulus, okay, could be used, okay, when we want to uh, analyze the result based on the SSI approach. Okay, so in relatively soft saturated near surface sediment, which is likely to be the case for a large number of geotechnical problems, the P wave is dominated by the bulk modulus of the pore field. Okay, the water is hard compared to the soil. Okay, so as the resultant P wave may be close to that of the pore field. Okay, when it is fully saturated, so the P wave is more is more is better to be used. Okay. However, if the soil is unsaturated, okay, which is there are no the water the pore is not be the pore is not be the void is not being filled with water. Okay, VP can range from that of the soil metric with no pore fluid to that for the saturated case. Okay, therefore the use of the VP to determine the properties of the soil is problematic. Okay, so PVs might well is not in, uh, is not proper to be used. Okay, uh, under the unsaturated condition. Okay. However, pore fluid do not carry shear stress. Okay, so in that case, okay, the use of the S wave is much more better. Okay, because it is stated here that the pore fluid do not carry shear stress. Okay, and water also doesn't carry any shear stress. Okay, we cannot shear the water. Okay, but we still can compress the water. Okay, it's only influenced by the soil and not by the pore fluid. Okay, so it can also be shown that during most dynamic loading event, it is cyclic change in shear stresses that influence the behavior of the soil. So that will be another advantage of using this S wave. Okay, because in the dynamic event, the cyclic from this dynamic event, okay, influence the shear stress. From the theory of the propagating wave, it can be shown that the wave velocity through the soil is related to the stiffness of the soil, okay, by G equal to rho Vs power by 2. Okay, so this is the shear modulus, okay, while this is the rho is the soil density, and this is the what we call as the shear wave. Okay, so from this equation, we can obtain the shear modulus value. Okay. Therefore, changes in Vs within the soil can be used to determine the small strain stiffness. Okay. And the measurement of S wave is commonly employed to determine the dynamic behavior of the soil at small strain. Okay. So this G, okay, is very important. Okay. When we want to determine the dynamic behavior of, of the soil at the small strain. So this example of the wave propagation, okay, under the P wave and under the S wave. So shear wave, a wave in which the disturbance is an elastic deformation perpendicular to the direction of the motion of the wave. Okay. So shear wave also called as a transverse wave. Compression wave, a wave in which the disturbance is compression of the medium. Compression also gets a longitudinal wave. Okay, so this is additional explanation on the shear and compression waves. Okay, the third wave that is frequently encountered in soil is the relic wave, which travel along the ground surface. Okay, so the relic wave measurement have gained in importance in the recent years since the ground surface measurement can be readily and easily undertaken without the need for any intrusive investigation. Okay, so as mentioned by the author, we can easily get the value for the wave, okay, on the surface of the soil. So I have a comment I need to answer first. Okay, so from the relic wave, okay, uh, there are some equation, okay, that can be used, okay, to determine what we call as the the Young modulus or the shear modulus, okay. However, we need to convert it, okay, from based on the Poisson ratio, okay. From there, uh, the equation from the VR, okay, can be converted to the VS by multiply with the 1.09. Okay, so therefore measurement of rally weight can give a good determination of shear wave velocity from which G can be derived. Okay, okay, so this an example of the relic wave. Okay, okay, so later on the use of the G, okay, is very important, okay, when we want, for example, to include for any seismic effect, okay, in the design, okay. For example, if you want to include the effect of the seismic in your software, for example, in Plexis, so you need to include the value of the G, okay, during your analysis, okay. However, I'm not very familiar, okay, because yeah, it based on uh, yeah, if for example, if uh, we uh, we may learn on this seismic effect, okay, when we have some when we have event need to consider for the effect of the earthquake or any vibrations, okay, but at the moment I didn't have any experience, okay, dealing with this kind of vibration or earthquake effect, okay, in any analysis that I have carried out, okay. But the G or the shear modulus is very important, okay, whereby we may use it, okay, when we want to include the vibration effect in the design to be included in the soil properties, okay. So can we take a rest for 5 minutes?
Okay, okay, bro.